Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hi Herman and Corin. So I really thoroughly enjoyed that episode about best practices in writing checklists and SOPs. And I have to say, for anyone who's been involved in this, professionally or personally, whether it's the context of preparedness or some other context, these are the guidelines that just never get talked about. And as you mentioned, so frequently little things are done poorly. We talked about the fact that these are often written by experts who are immersed in the subject matter, and usually that sounds like it can be a good thing, but too much knowledge sometimes works against us. So the comprehensiveness and the edge cases are what frequently makes it seem way too complicated. And those little tips you had about color coding, active verbs are golden. And so really thank you, Herman and Corin. That was terrific. I'm going to dust up my own documentation today for the rocket stuff, because I think I've followed some of your guidelines, but I've got work to do. So Herman and Corin, I'd like to chat today about move over to a slightly adjacent topic. In that episode, you mentioned Obsidian, which it's hard to make too much headway in wikis, digital knowledge, documentation without crossing path with Obsidian. And it's a very nice tool. It's very powerful, very modular, very customizable. But it has one feature that's always kind of turned me away from it, and that is that it's very much a local first tool. So Obsidian will sell you cloud storage so that you can sync your notes across devices, and you can hack around it very easily. You can have GitHub as you can version control a vault with GitHub, or you can just do a more simple Google file sync. Now, this is where I'd like to actually prise into the details a bit, because when we talk about sync clients for desktop, for services like Google Cloud or Google Drive, to take an example, or it could be Google Cloud Platform, but there's two very different ways of doing it. The first is what we might call a sync by replication client, in which the local user basically clones the entire remote file system. And that gives what feels like instantaneous performance because it's local. But every time you make some changes locally, it goes up to the remote. Now, there's one fatal flaw in this design, which is that you have to have more capacity locally than the cloud. So if you have a 8 terabyte cloud and you only got a 1 terabyte local storage, you have to select which folders to sync, and then that always gets a bit scrappy and messy because you end up creating a folder. Someone else creates a folder that you didn't sync, and it goes on like that. Now, that's the reason that I've always looked for what's called, I guess, volume syncs. I don't know exactly how these work under the hood, which is what I want to get into today. There's a wonderful tool on Linux called Rclone, which allows you to mount just about anything, whether it's NFS, SMB, S3, you name it, local, remote, it does it. And these work very differently at a fundamental level. You don't clone it, you just mount it. Now, that's my question, is what's actually going on if my mounted drive, let's say it's an S3 bucket for argument's sake, and it's much bigger than what I have on my computer, but when I mount it, I'm able to navigate through it, and when I open a file, it just kind of pulls it in. Now, it doesn't typically work as well, I find, as the local model, and sometimes on Linux in particular, it's very buggy, but it seems like a much more, it gets you around that very significant limitation of you have to have the capacity. So Herman and Corin, what's going on under the hood in these systems, and how does it differ exactly from the first? And are you able to get a truly fluid remote sync experience or is it something that's just inherent to the design that getting that to work well is very challenging? Vermin and Corn, over to you.
Hey everyone, welcome back to my weird prompts. I am Corn, and I am sitting here in our living room in Jerusalem with my brother. It is a beautiful afternoon here. The light is hitting the stone walls just right, and we have got a fresh pot of coffee ready for what I think is going to be a pretty deep technical dive.
Herman Poppleberry here. It is good to be back at the microphones. I have been looking forward to this one. My desk is currently a disaster zone of external hard drives and network cables because I have been doing some of my own experimentation with the very topic we are discussing today.
So, it sounds like Daniel really enjoyed our recent deep dive into standard operating procedures and checklists. He mentioned he is actually going to be dusting off his own documentation for his rocket projects, which is pretty cool. I love the idea of someone using our nerdy ramblings to help build actual rockets. But his prompt today takes us in a slightly different direction, though still very much in the realm of how we organize and access our digital lives.
Right. Daniel wants to talk about the difference between sync by replication, which is what most of us are used to with things like Google Drive, Dropbox, or OneDrive, and volume sync systems like Rclone. It is a great question because it touches on a fundamental trade-off in computing. Do you want your data to be local and fast but limited by your hardware, or do you want it to be remote and infinite but potentially sluggish?
Exactly. And Daniel specifically asked about how these volume sync systems work under the hood, and whether we can ever truly achieve a fluid remote experience. I think a lot of people have tried to mount a cloud drive using a tool they found on GitHub, felt that stutter or that lag when they tried to open a folder, and wondered, is this just how it is? Is the internet just too slow? Or is there something fundamentally broken in the design?
It is a classic engineering challenge. To really understand it, we have to look at how a computer thinks about a file. When you use something like the standard Google Drive client on a Mac or a PC, you are usually looking at a replication model. In that world, there is a literal physical copy of your file on your hard drive. When you change it, the client notices the file system event, calculates the binary difference, and uploads that change to the cloud.
And the big benefit there is speed, right? Because when I open a document, I am opening it from my own fast solid-state drive. The syncing happens in the background. My computer isn't waiting for a server in Virginia to respond before it can show me my own text.
Exactly. It feels instantaneous because, for the purposes of that interaction, it is a local file. The software is essentially playing a game of keep up. It is watching your disk and the cloud and trying to make them match. But as Daniel pointed out, the fatal flaw is capacity. If you have a 2 terabyte cloud account but only a 500 gigabyte laptop, you are playing a constant game of digital Tetris. You have to use selective sync to choose which folders are actually on your machine. It is a manual, high-maintenance way to live. You are constantly checking boxes and waiting for blue bars to fill up.
And that is where the volume sync or the mount model comes in. This is what Rclone does so well, and it is what power users often gravitate toward. Instead of copying the files and taking up space, it creates what we call a virtual file system, or VFSS. Herman explained to me how my operating system even knows how to talk to something like that. If there is no file on the disk, what is the computer actually looking at when I open that folder?
This is where it gets really clever and a little bit Matrix-like. In Linux and Mac OS, there is a mechanism called FUSE, which stands for File System in User Space. Normally, the file system is a very guarded, very sacred part of the operating system kernel. It is low-level, high-performance, and very rigid because if the file system crashes, the whole computer crashes. But FUSE allows a regular program, like Rclone, to tell the kernel, hey, I am a file system. If any application asks to see the contents of the folder /mnt/cloud, don't look at the hard drive. Ask me instead.
So Rclone is essentially acting as a translator or a middleman. When I open my file browser and click on that mounted cloud folder, my computer sends a request to the kernel saying, show me the files in this directory. The kernel then passes that request to Rclone.
Precisely. And Rclone says, hold on one second. It then makes an API call over the internet to Google Drive or Amazon S3 or whatever service you are using. It asks the service for a list of files in that specific remote directory. Once it gets that list back, it formats it in a way the operating system understands and hands it back. To you, the user, it looks like a normal folder with normal icons. But in reality, nothing was there until the moment you asked to see it. It is just-in-time data delivery.
I can see why that would be a bit slow. If I have a folder with 10,000 files in it, Rclone has to wait for the cloud API to respond with that massive list before I can even see the icons on my screen. That is a lot of metadata to fetch over a wire.
That is exactly the first bottleneck, metadata latency. Every time you list a directory, do a search, or even just right-click a file to see its size, you are triggering a round trip to a server that might be thousands of miles away. Even with a fast fiber connection, you are looking at maybe 100 or 200 milliseconds of latency. In computer time, that is an eternity. A local hard drive would respond in less than 1 millisecond. When you multiply that by hundreds of files, you get that spinning wheel of death, or the window that just hangs while it populates.
So that explains the lag when browsing. But what about actually opening a file? If I have a 10 gigabyte video file on a mounted Rclone drive and I double click it, surely it doesn't have to download the whole thing before the player starts? If it did, it wouldn't be much better than the replication model.
That is the magic of the VFS layer in Rclone. It supports something called range requests. If you open a video file in a player like VLC, the player doesn't actually need the whole 10 gigabytes at once. It just needs the first few megabytes to read the header and start the stream. Rclone tells the cloud provider, hey, give me the data for this file starting at byte 0 and ending at byte 5 million. The cloud provider sends just that tiny chunk. Rclone hands it to VLC and the video starts playing almost immediately.
That is fascinating. So it is essentially streaming the file on demand, much like YouTube does with video. But I imagine this gets complicated if the application wants to write data, or if it keeps jumping around to different parts of the file. A video player is linear, but a database or a code editor isn't.
Oh, it gets incredibly complicated. This is why Daniel mentioned that these systems can feel buggy. Think about how a complex application like Photoshop or a video editor like Premiere works. They expect the file system to be perfectly reliable and incredibly fast. They are constantly writing temporary scratch files and updating headers. If Photoshop tries to write a small change to a header in a large file and the network connection blips for half a second, the application might just crash or report a corrupted file. It doesn't know it is talking to a cloud server. It thinks it is talking to a local disk that has suddenly gone insane.
So, to make this fluid, Rclone must have some kind of caching strategy, right? It can't just be a raw pass-through for every single byte, or it would be unusable for anything other than simple file copies.
You hit the nail on the head. Caching is the secret sauce, and it is also where most of the configuration complexity lies. Rclone has several VFS cache modes. The most basic mode is off, which does almost no caching. It is very safe because you know exactly what is on the remote, but it is painfully slow. Then you have modes like writes, where it caches files locally only while they are being written to, and then uploads them once they are closed. This helps with the Photoshop problem I mentioned.
But for a truly fluid experience, like Daniel is asking about, you'd want a full read and write cache, wouldn't you? Something that makes the cloud drive feel like it has a local brain.
Exactly. Rclone's VFS cache mode full is the gold standard for a smooth experience. In this mode, Rclone keeps a local cache of the chunks of files you have recently accessed. If you watch the first 5 minutes of a movie, those 5 minutes stay on your hard drive. If you go back and rewatch a scene, it loads instantly from the cache. It also handles writes by saving the changes locally first and then uploading them in the background. It bridges that gap between the replication model and the mount model. It is essentially a hybrid.
So if I have a 50 gigabyte cache set up on my laptop, I can have an 8 terabyte cloud drive mounted, and Rclone will just keep the most relevant 50 gigabytes of data on my machine at any given time. It is like a sliding window into my entire cloud library.
That is the dream. It is essentially an LRU cache, which stands for least recently used. When the cache gets full, it starts deleting the oldest, least accessed chunks to make room for new ones. When it works, it is beautiful. You get the feeling of infinite storage with near local performance for your active files. But, as Daniel asked, is it truly fluid? Why does it still feel less than perfect sometimes? I have noticed that even with a good cache, sometimes my file explorer will just hang for a few seconds.
Yeah, why is that? If the data is cached, why the hang?
There are a few inherent ghosts in the machine with this architecture. The first is what I call the directory traversal tax. Even if you have the file data cached, the structure of the folders often isn't. If you have a deeply nested folder structure, just navigating into a subfolder can trigger an API call to check if anything has changed on the remote side. You can tune this with something called the directory cache time, telling Rclone to trust its local map of the folders for, say, an hour instead of checking every time. But then you run into the sync problem. If you added a file via your phone, it won't show up on your computer for an hour.
The classic cache invalidation problem. One of the two hardest things in computer science, right alongside naming things and off by one errors.
Exactly. And the second issue is file locking. Local file systems are very good at making sure two programs don't try to write to the same file at the exact same time. Cloud APIs are generally not designed for that kind of fine-grained locking. If you have an Rclone mount on two different computers and you try to edit the same Word document at the same time, you are going to have a bad day. The cloud provider will usually just accept whoever finished the upload last, and the other person's changes are gone. There is no file in use, warning like you get on a local network.
That sounds like a nightmare for collaborative work. So this volume sync model is really better for single user access or for media consumption where you aren't doing a lot of simultaneous writes from different locations.
Precisely. It is why you see Rclone used so heavily in the media server community. If you have a massive library of movies on an Amazon S3 bucket or Backblaze B2, using Rclone to mount that bucket to a Plex or Jellyfin server is a match made in heaven. The media server sees a normal local folder, it can scan the files, and when a user hits play, Rclone just streams the bits on demand. It is much more efficient than trying to sync 50 terabytes of movies to a local server.
I want to go back to something Daniel mentioned about Linux specifically. He said it can be particularly buggy there. Is that a FUSE issue or is it something else? I always thought Linux was the king of file systems.
It is often a combination of FUSE overhead and how the Linux kernel handles what we call wait states. When a program asks for data and that data is coming from a remote mount, the program enters a disk wait state. In Linux, this is often shown as the D state in a process monitor. If that wait takes too long because of a network hiccup or a slow API, the process can become uninterruptible. You might have seen this where you try to kill a process with the kill -9 command and nothing happens. The process is just stuck waiting for a response from the file system that might never come.
I've definitely seen that. It is incredibly frustrating. You end up having to unmount the drive forcefully using umount -L, or even reboot the whole machine just to get control back. It feels like the whole OS is held hostage by a single slow packet.
Exactly. And because Rclone is a user space program, if the Rclone process itself crashes or gets hung, the mount point it created becomes a sort of zombie. Any other program that even tries to look at that folder, even just a background service, will also hang. This is the inherent fragility of the mount model. You're introducing a massive, unpredictable dependency, the internet, into the very core of how your computer operates. A local disk might fail, but it fails in a predictable way. The internet fails in 1,000 creative ways every day.
So, is there a way to make it better? Are there alternative designs that don't rely on FUSE? It seems like FUSE is the bottleneck because it requires the CPU to constantly switch between the kernel and the user space program.
There are kernel-level implementations for some cloud protocols. For example, there is a kernel driver for CIFS and NFS, which are traditional network file system protocols. Because they live in the kernel, they are much more performant and stable. But the problem is that cloud providers like Google and Dropbox don't speak NFS, they speak HTTP and REST APIs. They were built for web browsers, not for operating system kernels.
So we are stuck with a translation layer. We are trying to fit a square peg in a round hole.
For now, yes. However, There is a newer technology called Microsoft Project Reunion, or now known as the Windows App SDK, and similar initiatives in the Linux world like GVFS or KIO that are trying to create cloud sync providers at the OS level. The idea is to give the operating system a native way to understand that a file is online only without needing a fake virtual disk. This is how the modern OneDrive and iCloud clients work. They aren't mounting a drive in the traditional sense, they are integrated into the file manager itself.
That seems like a much more robust approach. The file manager knows the file is remote, so it can show a little cloud icon and handle the download gracefully without freezing the entire interface. It can say, downloading, instead of just hanging.
Exactly. It is asynchronous by design. The problem is that these APIs are often proprietary and locked down. Rclone is wonderful because it is open source and supports over 40 different providers. It gives you that power for any service, from a high-end S3 bucket to a cheap Mega account, but the trade-off is that it has to use the older, more brute force method of FUSE mounting to stay compatible with everything. It is the price of freedom, I suppose.
I wonder if we will ever see a standardized cloud file system protocol that everyone adopts, something that has the performance of NFS but the flexibility of a web API. It feels like we are still in the wild west of cloud storage.
People have been trying to make that happen for decades. WebDAV was supposed to be that, but it is notoriously slow and limited. There are newer efforts like the Interplanetary File System, or IPFS, which uses a peer-to-peer model, but that is a whole different rabbit hole involving content addressing and distributed hash tables. For the average person today, the best fluid experience is actually a hybrid.
What does that hybrid look like in practice? If Daniel wants to set this up for his Rocket docs, what should he actually do?
It looks like using a high-quality mount client like Rclone with a very well-tuned VFS cache. If you give Rclone enough local disk space for a cache, say 100 gigabytes, and you tune your buffer sizes and look-ahead settings, you can get very close to a local feel. You also have to be smart about your checkers and transfer settings. If you tell Rclone to check for changes too frequently, you will hit API rate limits and everything will grind to a halt.
That is a good point. I have heard stories of people getting their accounts temporarily banned because they had a script scanning their mounted drive every 10 seconds, and the cloud provider saw that as a distributed denial of service attack. Google Drive is particularly sensitive to that.
It happens more often than you'd think, especially with providers like Google Drive that have very strict queries per second limits. To get a fluid experience, you actually want to be less aggressive. You want to tell Rclone, hey, don't check the remote for changes unless I specifically ask, or only do it every 30 minutes. You rely on the cache to provide the speed, and you accept a little bit of staleness in exchange for stability. You can also use things like Rclone RC to manually trigger a refresh when you know you've added a file.
So for Daniel, who is dealing with Rocket documentation and potentially large datasets, the takeaway might be that there is no magic button for a perfect remote sync. It is all about how much local disk space you are willing to sacrifice for a cache. The more you give it, the more fluid it feels.
Exactly. If you want it to be fluid, you have to give it a landing pad on your local drive. Think of it like a buffer in a streaming video. If the buffer is too small, the video stutters every time the network fluctuates. If the buffer is large, you don't even notice the network blips. A volume sync mount is just a giant, persistent buffer for your entire file system.
I want to go back to something Daniel mentioned about S3 buckets. Is there a difference in how a mount performs if it is talking to an object store, like S3 versus a drive, service like Dropbox? I know they feel the same in the File Explorer, but they must be different under the hood.
Oh, absolutely. That is a huge distinction that many people miss. Object storage like S3 or Backblaze B2 is not a file system. It has no concept of folders really. It is just a flat list of keys and values. When you see a folder in an S3 bucket, it is actually just a naming convention. The file isn't in a folder, the file is just named folder/subfolder/file.txt.
So when Rclone mounts an S3 bucket, it has to do a lot of heavy lifting to pretend that those keys are a directory tree. It has to parse all those slashes and build a virtual map.
Yes, and that makes operations like moving a folder incredibly expensive. In a real file system, moving a folder is just a metadata change. You're just changing a pointer. It takes a fraction of a second. In S3, moving a folder means renaming every single object inside that folder. If you have 10,000 files, Rclone has to send 10,000 copy commands and then 10,000 delete commands. If you do that on a mounted drive, your computer will look like it has completely frozen while Rclone chugs through those 20,000 API calls.
Wow. So the lie that the mount is telling becomes very transparent when you do something that a real file system is good at, but an object store is bad at. You're trying to do a metadata operation, but the back end is doing a massive data operation.
That is the perfect way to put it. It is a useful lie, but it has limits. If you are using Rclone with S3, you have to train yourself not to do massive organization changes through the mount. It is much better to do those through a dedicated tool like the Rclone command line or the provider's web interface. Use the mount for reading, writing, and small edits. Don't try to reorganize your entire archive by dragging and dropping in Finder or Windows Explorer.
This brings us back to the question of whether a truly fluid experience is possible. It seems like the bottleneck isn't just the network, it is the fundamental mismatch between how we want to use data as a hierarchy of files and how that data is actually stored in the cloud as a massive flat sea of objects.
I think that is the core of it. We are trying to force a 20th century model of files and folders onto 21st century distributed object storage. To get a truly fluid experience, we might need to move away from the idea of a mounted drive altogether and move toward applications that are cloud native, meaning they know how to talk to the cloud directly and handle their own caching and latency.
Like how Spotify does a mount, a music folder on your computer. It just knows how to stream music and cache it locally. It handles the buffer itself because it knows exactly what kind of data it is dealing with.
Exactly. Or how Google Docs doesn't need a local file, it is just a direct interface to the data. But for general purpose computing, where we want to use our favorite local tools like VS Code, Photoshop, or Daniel's rocket design software, we are stuck with these bridge technologies like Rclone. And honestly, considering the complexity of what it is doing, I think Rclone is a bit of a miracle. The fact that I could mount a bucket in Amsterdam from my desk in Jerusalem and it works at all is pretty incredible.
It really is. I think for anyone listening who wants to try this, the key is to start with the Rclone VFS S-Cache settings. Don't just do a basic Rclone mount. Take the time to read the documentation on VFS cache mode full and VFS cache max size. It makes a night and day difference. Also, look into the ATTRA timeout flag, which tells the OS how long to remember file attributes like size and modification time. Setting that to a few minutes can drastically speed up browsing.
And maybe don't put your entire operating system on it. Keep your core apps and configuration local on your NVMe drive and use the mount for your cold or warm data, the stuff you need to access but don't need to be editing every second. Use it for your archives, your media library, or your historical documentation.
Good advice. So, to wrap up the technical side, the mount model via FUSE is a translator that turns cloud API calls into file system operations. It is inherently prone to latency because of the network, but clever caching can mask a lot of that. The bugginess usually comes from applications expecting a local disk's speed and reliability, and getting frustrated when the cloud doesn't deliver.
Spot on. And for Daniel, I'd say, yes, it is challenging to get it working well, but with enough local disk space for a cache and some patience for the initial directory indexing, you can get a very usable, almost fluid experience. Just don't expect it to behave like an internal drive. Treat it with a bit of respect for the thousands of miles the data has to travel.
Well, this has been a great dive into the plumbing of the internet. I feel like I understand why my computer sometimes gets the spins when I am trying to access my cloud archives. It's not just a slow connection, it's a complex dance of kernel requests and API calls.
It is just the ghost of the internet trying to catch up with your mouse clicks.
Before we sign off, I want to say a huge thank you to everyone who has been listening. We have been doing this for 758 episodes now, and the community of weird prompters out there is just fantastic. We've gone from talking about standard operating procedures to the intricacies of FUSE file systems, and you're all still here with us.
It really is. We love getting these questions that push us to look under the hood of things we often take for granted. If you are enjoying the show, we would really appreciate it if you could leave us a review on your podcast app or on Spotify. It genuinely helps other people find the show and keeps us motivated to keep digging into these topics. It's the best way to support what we do.
Absolutely. And remember, you can find all our past episodes, show notes, and a contact form at myweirdprompts.com. We also have an RSS feed there if you want to subscribe directly and avoid the algorithms.
If you have a question or a topic you want us to tackle, whether it's about rockets, file systems, or anything in between, you can reach us at show@myweirdprompts.com. We would love to hear from you.
This has been My Weird Prompts. We are available on Spotify, Apple Podcasts, and wherever you get your podcasts.
Thanks for listening, and we will catch you in the next one.
Goodbye, everyone.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.